Okay, so today's topic is on map symbology. Last week we talked about some general GIS topics, and one of the things we talked about was how we store our GIS data as features on a map. We store them as points, lines, and polygons, are the common types of features that we use to model real-world objects in our GIS. And map symbology is how we distinguish between a point that's a manhole and a point that's a fire hydrant, or a line that's a road, or a line that's a stream. We symbolize them in different ways. So map symbology is the topic for today. Some learning objectives. We'll choose symbols to use for point, line, and polygon features. We'll modify some different properties of symbols, such as color, size, and outlines. We'll also label features on a map using attributes, as well as just by manually adding text to the map. We'll symbolize features to show type, rank, and amount. We'll group features into classes and apply symbols to each class. We'll compare different methods for grouping features into classes, correct visual distortion caused by differences in the area of features. We'll show proportional amounts on a map by normalizing data, and we'll also symbolize features to show density. So map symbology, one definition of it, or one thing we say about it, is it's the combination of symbols, colors, and text that make up a map. By using effective symbology, we make maps easier to understand. So when people look at a map, if it has effective symbology on it, they're easier to take away the meaning of the map. Meaningful and intuitive symbology also make maps more effective in general. So here are some examples of map symbology. This is a symbol psychology slide where some of these make sense and some of them don't quite make as much sense. In this case, the polygons in the background represent amounts of rain throughout a landscape, and the towns are points. So it's supposed to show that the darker areas have less rain than the blue areas on the right side, and it should be a little bit intuitive for red being dry or hot, that kind of thing. The bigger points should also be a little more intuitive, that they have more people. So in this case, we're using some colors to shade different polygons to show different amounts of rain, and we're using different sizes of points to show different amounts of people in a city. So a couple different properties of symbols we're changing there is color and size. This one over here, we're actually changing the symbol to maybe look like a school or a hospital. So those symbols represent based on a shape. Down here, where's the water in this? This kind of is meant to show you that not using intuitive colors and colors that people associate with certain things can make a map real confusing. So where's the water in this map? Well, the water is actually not the blue, and when you first look at it, it's confusing to the eye because you're used to seeing blue as water, and it shows you, if you don't pay attention and if you're not intentional in your map symbology, you can make maps that are confusing. Where's the danger? We often associate red with danger. So symbolizing is assigning, and we're talking about assigning appropriate colors, markers, sizes, widths, angles, patterns, transparencies to vector features as well as to rasters. And we assign all these things to help distinguish the representation of points, lines, and polygons and rasters on a map. The way we symbolize data can be influenced by scale. We can symbolize single features. We can symbolize everything in the map the same way, or everything in a layer the same way. Or we can symbolize within a layer based on attributes that are either categorical or quantitative. The example on the left shows us symbolizing some counties. It's in South Carolina, Georgia, and North Carolina there. And on the left, it shows us symbolizing all the counties with a single symbol. On the right, we're symbolizing using unique values where each county gets a different color. That's called a choropleth map when we use colors to distinguish between features on a map like that with polygons. So when you load data into ArcMap, the default method ArcMap uses to symbolize the features is that it symbolizes everything the same within a layer. So it doesn't distinguish between features in a layer that have different attributes associated with them. Remember, an attribute is a descriptive piece of information about a feature on a map. So here's an example similar to that of the counties, where we're symbolizing by state names used to show different features. And here we have symbolized based on region or subregion. So you can imagine each polygon in this layer has a name attribute, and it also has a subregion attribute. So for West Virginia, Virginia, North Carolina, South Carolina, Georgia, and Florida here, they all have the same value for subregion. It's probably southeast. As I just mentioned, in ArcMap, the default operation when you load a layer is all the features get the same symbol. So the same color, the same point, the same line symbol. In this case, all features, the example 2 slides before, here, when you load into ArcMap a counties layer, all the counties get the same symbol. We symbolize features in ArcMap, and when we save a map document, that symbology is saved with the map document. So the symbology is not saved with the layer. The layer is just simply polygons or points or lines, and they store information about those features, and it stores coordinates for where the features are on the Earth, but it doesn't store different symbols for it. We've got two broad types of maps that we think about. General reference maps have a focus on the location of features, and they're used for general reference. A general reference map, an example of one, is a USGS topo map. It's got lots of different types of features on it. It's got county boundaries and contours and roads, probably some buildings, national forest. It's got a lot of different types of information. Hydrography, water layers. A thematic map has its focus on the distribution of one or more phenomena or attributes. So a thematic map, an example of it, is something like a weather map that has mostly weather-related information on it. So no maps are 100% thematic. There's always a little bit of general reference information, just so you know where you're looking at. If you don't have any general reference information, you won't be able to relate the weather to where it's happening. So here's a couple examples. The one on the left is a general reference map. It shows cities, state lines, roads, water bodies, lots of different information. On the right, it shows a thematic map, which is a precipitation map, it looks like. So effective map symbology should play on people's associations with real-world phenomena. You should use blue for water, green for vegetation, thicker lines for busier roads, things like that. People will understand looking at the map without having to think about it. it'll naturally make sense to them. We also combine textual information with symbology to help convey a full picture of what we're mapping. Symbols and text are often based on the information in the attribute table that we are mapping. Here you can see some different symbol types that we use to map different types of features. So properties can be changed of features to create symbology. For points, we'll often change the symbol or the color, angle, and size. These are all what we refer to as symbol properties or visual properties, the things that we can change about them to help distinguish between different points that mean different things. With lines, we change the symbol, the color, the width. With polygons, we can change the fill color. We can add a pattern to the inside of the polygon. We can change the outline color, width, or even the background color. So you can see for different feature types or different shapes, they have different properties that you can change. So I mentioned that symbology is saved with the map document. So when you load data into a new map document and you've spent time symbolizing it in one before, you don't have that symbology anymore. Those counties just get loaded in with a single symbol by default again into a different map document. And you have to spend time symbolizing it again. So you can actually save symbology outside of a map document in something called a layer file. It has a .lyr extension. And this is different than the generic term layers that we talked about last week. In a GIS, we've always talked about layers of information, and we overlay them on the map. Okay, so layers in GIS is a real generic term. We use it to refer to any kind of data that we overlay in ArcMap, whether it be an aerial photograph, CAD data, GIS data, any kind of GIS format. Anything we load into ArcMap is a layer, just generically speaking. A layer file is different. A layer file is a way to store symbology inside of ArcGIS for a layer, and it also points to the data that it references. So it's kind of like a map document in that it doesn't store the data in itself. With a layer file, you also need the data. A layer file is no good without the data that it references. All a layer file does is it stores symbology, and it stores a path to where the data is that it's symbolizing, a lot like a map document does. Saving symbology in a layer file ensures standard symbology is used across maps within an organization, and that's pretty powerful. So if you want your roads to be symbolized the same way on every map, using a layer file will ensure that everyone symbolizes it the same way. I was talking to someone at Metropolitan Sewer District this week, and they were talking about how different people in their organization make different maps, and they make decisions based on these maps. And one person was symbolizing, it had something to do with the private sewer lines versus the public sewer lines, and they pay to maintain, I guess, the public ones and not the private ones. And someone called about a sewer line, and they were looking at a map that had them symbolized the opposite of how they were symbolized on other maps. And so they made a decision based on it being public when it was actually private, and it had to do with map symbology and it not being consistent across the organization. And of course, there was a key on the map that the person could have looked at, but just real quick, someone called and they were trying to answer a question, and so they made a decision based on a map that was not symbolized in a consistent way with the rest of them in the organization. So where you get these symbols, ArcGIS has thousands of them to choose from. We organize them in ArcGIS into something called a style, and ArcGIS comes with a bunch of predefined styles. Some are general purpose, some are industry specific. There's a bunch of water and sewer styles. There's styles for forestry and styles for electric utilities, transportation. You can also create your own styles. So there's literally thousands of styles. You can create your own style, and you can pull from existing styles and make your own. You can also create your own symbols. So it's kind of useful to create your own style. Sometimes you'll create a style and it will, if you have one map that you've got a bunch of different symbols going in, you'll create a style for that map. And it makes it easier to find styles when you've got thousands of them if you create your own style and put what you use often into a style. At version 10, there's also a search functionality for styles, for symbols within the style area. Here's a couple examples of symbols. They can be replicative or abstract. The first is designed to mimic real-world features. You can see a snowflake or a fire hydrant or a picnic bench. The others are abstract geometric shapes. Say we use squares to represent parks and circles to represent cities, something like that. And you've got a legend that tells you what they stand for. You have to be a little bit careful using symbols like this one that are actually a bitmap. They'll cause your map to draw a lot slower and things like that. And when you've got 3,000 fire hydrants on a map, maybe a little picture that looks like a fire hydrant's not the best idea. It just clutters up the map. Just a little red dot might be a better technique for symbolizing when you've got thousands of features. So, labeling map features. Text can serve many different functions on maps. We often use text to label or describe a feature, like the name of a town. We use text from attribute tables. We label features with text from attribute tables often. We can also just manually add it to the map. So it's pretty powerful in a GIS when you're making a map of the entire United States and it's got a lot of the major cities on it. You can automatically put a piece of text on the map for every city using the label function. It's a lot easier than going through and typing it manually on the map. It will automatically label features based on information in the attribute table. Sometimes you don't have a feature though, and you need to type on a map. An example might be when there's a mountain range or a ridge across a map, or there's not necessarily a feature there. I think we have an example of that here, the Blue Mountains. So when you go to, if you have some data, like in this case, all of these triangles in this graphic are mountain tops. If you ever have some data and you want to label it based on, say, the name of the mountaintop here on these triangles, and you look in the attribute table and the name's not in the attribute table, you don't have the information that you want to label it. It makes more sense to spend the time populating the attribute table and then labeling it using the attribute table than to spend the time just manually typing them on the map. Because once they're in the attribute table, you can reuse them in other maps. So populating attribute tables is usually worth the time. So the term annotation is used when we think of text that's manually added to a map. You can store it in either the map document or in a database. And we use annotation when we need finer control over the placement of labels. So the labeling feature in ArcMap, when you label features based on information in the attribute table, is really powerful because you can label a lot of features at one time. But you don't have a lot of control over the exact placement. ArcMap has a labeling engine, and it decides where to place labels. And it uses conflict detection to try not to put it on top of other features. It tries to put it away from other labels. And when you start getting a map with a lot of features and a lot of labels, sometimes you need to tweak individual ones. And so annotation is often used to do that. So the two big types of ways we use text on maps. One is labels, labeling features based on an attribute table. The software handles the placement of it. It's good because you can do it in bulk. You can change all the properties of the text at one time. You can make it all bigger. You can make it all a different color. Annotation is a little bit more time consuming, but you have finer control over it. So, types of data, we said that we use information in the attribute table to symbolize features. Two broad types of information we store in attribute tables. You can store categorical data, which is descriptive type textual information. In this case on the left, it's probably type of geological structure or something like that. Maybe forest type, soil type, where there's, if it's forest type, it'd be whether it's an oak forest or a hardwood or a pine forest. Quantitative data is numeric data. Things like population, amounts of rain, stuff like that. So whether you're symbolizing categorical data or quantitative data, you have different symbology techniques that you use, and you change different properties of the symbols depending on which type of data you're symbolizing. So thematics maps use features to symbolize features symbolized by attributes. Thematic maps communicate more information that show feature locations alone. So a thematic map with symbology will tell you more than a map that's not symbolized based on the attributes. Attributes can be non-numeric, like we mentioned, or they can be numeric. So here is an example of two maps and how it's the same data, okay? And one shows you a lot more than the other one. The example here on the left is where all of the vegetation is symbolized with the same symbol. It doesn't matter what kind of vegetation it is, the polygons. And all the pine trees are symbolized the exact same as well. But if you look over here, in the attribute table for vegetation, there's information that's stored with each polygon about what type of vegetation it is. And in the attribute table of the pine trees, there's information stored about the diameter of each tree. So for the vegetation, they've changed the colors and even a pattern in the polygons to show different types of vegetation, and they've changed the size of trees to show you where the biggest trees are. It starts to paint a much better picture to you. You can see that the big trees are growing in the forest. There are no trees growing in marshlands, and the grassland has a couple trees, but they're smaller. So you can start to visually see some relationships between trees and the types of vegetation where they're growing because of effective use of symbology. So when we draw features to show category attributes are names, types, or ranks. The examples in the table to the right can be seen. There are examples in the table to the right, as well as some examples in the map here. So here you see water bodies is a layer, name is an attribute. That's non-numeric, categorical. And the examples of the names are things like Lake Michigan, Quabbin, Reservoir, Moose Bay.
A layer that has data collection stations has an ID attribute. Here are some values for that ID attribute. That's when you're just storing names. When you're storing types, stores and zones have different types of things stored in them. And then ranks are starting to be kind of similar to numeric data because they imply some kind of number, but they're not really numeric. Ranks are good to poor, large to small, first, second, third, that kind of thing. So with categorical data, we store names, types, ranks that are all non-numeric information. When we're drawing features to show quantities, quantity attributes are always numeric. These numbers represent counts, amounts, rates, or measures. So the table to the right shows some examples of these. Things like population, revenue, literacy rate, depth. All of these are numeric types of information. For a water system, it might be flow rate, pipe diameter, things like that. When we draw features to show quantities, they're typically mapped by creating groups or classes of features with similar values. We assign a different symbol to each class, and we change the symbol gradually from one class to another. Graduated size and color are two common ways to symbolize quantities, and it's important to be aware of common color associations that people make. Things like blue is cold and orange is warm. Here's an example that shows population within Italy, some different provinces, and what they've done is they've grouped polygons that have similar values into this yellow class between 120,000 and 2.5 million. These polygons that are yellow have been grouped into that class. So what we said up here is that we map quantities by creating groups of features with similar values. So the provinces that are in yellow we've grouped because they have similar values of population. They have a close to the same population. So you can see we made four different groups. Even though there's many more than 4 provinces, we made 4 groups and we lumped everything into them. And then we mapped it with a range of colors from yellow to red, cutting through a little orange there. So when we map quantities, you have to decide how many classes you're going to map, how to place values into those classes, basically where you're going to split the classes, and what symbol you're going to use. This is a graduated color kind of thing. A graduated symbol would be a small symbol to a big symbol. And we do that often with populations of cities, where you're mapping based on the population of a city tied to a point. Alright, so when we say we have to decide where to split the classes, that's where you have to decide the classification method that you're going to use. Okay, so there are some common classification methods on this slide, and there's a couple others that you'll see when you go into mapping quantities. So natural breaks is the default classification method when you're mapping quantities in ArcMap. And it identifies natural breaks in the data, and it clumps things into groups based on natural breaks in the data. Equal interval, it's like a ruler. The interval between each class is the same. So you might have classes with intervals of 10%, 1 to 10%, 11 to 20%. Quantile is when each class contains an equal number of features. For example, you might have 15 provinces grouped into 3 classes. Each group would have 5 provinces each. And manual is when each class has a range that you specify. So you want to specify on an elevation model that it breaks at 2,300 feet, and then again at 3,700 feet, and then again at 4,400 feet for whatever reason. So which one of those should you use? There's no one answer. It depends on the characteristics of your data and the distribution of your data, the purpose of your map, as well as cartographic considerations of how easily a map is to understand. What you should do is look for patterns in your data, and you should try different methods and visually analyze the resulting map. So with any set of quantitative information, you can choose whichever one of those classification methods you want. And it's one way that we can be misleading, either purposely or not purposely, with maps, because each one will group features differently into different groups. And so it can make maps hard to understand, it can make them misleading, and that can be on purpose or not. So similar to how you can lie with statistics, this is one of the ways that you can lie with maps. And just like the book, How to Lie with Statistics, there's a book called How to Lie with Maps. And it's kind of a similar thing. The classification histogram is a way to try to understand your data before you map it. So we said to choose your classification scheme by looking at patterns in your data and mapping it, and then visually trying to see if it makes sense to you. This is a way to look at your data before you map it. So you can evaluate classification schemes before you map them. It charts the number of attributes or features for each attribute value. The bottom axis shows attribute values. In this case, it's from number 42 to 2,574. And on this side shows the frequency of the values. And this shows how many features, the gray bar indicates how many features fall between two of these lines within a classification. So this shows you that you got a bunch of features in this group. You got to give me features in this group and not as many features in this group. Here are some guidelines to classification schemes. Use the natural breaks method when attributes are distributed unevenly across the overall range of values, and it'll pick out breaks. Use equal interval when you want all the classes to have the same range. Use quantile when attributes are distributed in a linear fashion. And use manual when you want to break the classes where you want them to be, where you have a specific reason to group a certain set of features in one class versus a different. When we map density and proportion, we do this because polygons that vary greatly in size can be misleading. They can seem like they have more people when actually for the size, what they have more of whatever you're mapping, not more people, more of whatever you're mapping in a polygon, but it's such a big area that per square ground unit, it's actually not as many of what you're mapping. So patterns may be perceived as differences in attributes being mapped when actually it's differences in the area of the features. So by mapping densities, dividing the quantity by the unit area, we can avoid misperceptions. You see this kind of stuff with census data all the time. How many people per square mile live in an area? So when you think about people living in a place, maybe Asheville has a lot of people for a small area, when if you had where there's 70,000 people or something like that in Asheville, I believe. And it's kind of a small area. If you put 70,000 people in the whole state of South Carolina, it wouldn't be that many people. So it depends on the size area of what you're mapping. And it can be misleading if you're not mapping based on densities. So here's an example with all of the features symbolized the same here. And in this example, the orange has 10 goats in it, and the lighter color has 5 goats. So it kind of looks like from the color and that there's more in this area than these, when actually there's more for one unit, but that unit's much bigger than these areas. So if you map density, there's actually 2.5 goats per hectare there, where there's 5 goats per hectare here. So mapping density can avoid misperceptions based on the size and area of features. To map density, we use data normalization. Data normalization is basically dividing one attribute by another. It's one way to map density is to divide the attribute value by the area of the given polygon feature. In ArcMap, you choose the attribute field and an area field, and it automatically calculates the density. New values are used for symbolizing, but they're not actually stored in the attribute table. So there's a technique for doing this without actually changing any of the data in your attribute table. So after you do that, you still need to choose the classification method, the number of classes, and the symbolization method. And you'll see that in the exercise. When you normalize data to map density, you have to make sure that the data contains counts of some sort. And you also want to make sure that the attribute fields have not already been normalized. You don't want to normalize something again. If you're looking at census data, there'll be an attribute in there that's normalized already. We also map density visually through something called dot density maps, where we use dots to represent quantities of things in the real world. Each dot on one of these maps represents a specific count or amount. The more the dots, the greater the quantity. The closer the dots, the greater the density. But understand that an individual dot is not associated with an actual location. So in this example, we've got dots that represent 50 children that are under 18. Each dot represents 50. You can change that number. The more the dots, the more the children. The closer the dots are, the denser they are. The attributes are associated with these polygons. Okay, when we think about the features you're mapping polygon features here. There aren't any points. We're mapping polygons that have attributes associated with how many children live in each polygon, but we're using a dot density map to visually show that. It's a pretty standard technique, and it's not very hard to do in the software. The final thing that we map is proportions. Proportions are when you're mapping the relationship between two attributes. And it's similar to normalizing because you're dividing one attribute by another to produce a ratio, but it's not necessarily dividing the area. When you divide the area, you're mapping density. When you divide one attribute by another that's not necessarily area, you're just looking at the proportion of two things. So we typically symbolize these things using graduated colors. Proportions can be represented either as ratios arranged between 0 and 1, percentages, which are ratios multiplied by 100, or rates that are based on a round number, something such as a capita per person, per 100 or per 1,000. And this example shows we're mapping the proportion of people under 18 to over 18 just by dividing the two fields. So maybe proportion of men to women.
is another example.